Hello guys, again this is Sir DV giving you a continuation of the lecture on the theory of vibration. So we are now on the third and fourth types of vibration, which is the force and dump and the force of vibration. So for the force and dump vibration, so all we need to take note is that the differential equation of motion is quite similar to the free and dump vibration. The only problem is there exists now a right hand side, a value of the right hand side of this equation. So what we're going to do now is to first assume a homogeneous solution in the form of this equation. So you call this now a homogeneous equation, and make a second solution, which is called the particular solution, considering the effect of the non-homogeneous right hand side. So when you say homogeneous, we are now simply referring to the value of the right hand side, which is 0. Okay, so the homogeneity of such an equation makes it so when the right hand term is 0, and if the right hand term is non-zero, then it is now a non-homogeneous differential equation. So in this regard, we will be solving two solutions and make a complete solution by simply having a complementary and a particular solution, which if we add will result to a complete solution. Okay, so we already solved the complementary solution because we are already finished with this homogeneous case, which is actually the free undamped vibration. So this is the free undamped vibration. So all we need to solve now is the particular solution that will involve a non-homogeneous right hand side. Okay, so we're dealing with some sub cases or sub scenarios wherein the right hand side can be harmonic, etc. Okay, so first we assume that the right hand side is a harmonic loading, meaning to say it involves a sine or cosine or a combination of sine and cosine function. So this is now a harmonic function. Therefore, again, we don't need to determine the solution of yc because it's already done on the free and damp case. So what we need is to determine the solution of yp for the non-homogeneous term. And take note that every time you see a non-homogeneous right hand side, all you have to do is to pattern the solution on the nature of the right hand term, which is a harmonic solution. So we now make use of a solution that is of the same form of this harmonic solution. Hence we come up with a sine and cosine solution. So this is a harmonic solution which is only in terms of the sine function, and the complete harmonic solution is actually a combination of a sine and a cosine. So it's better to assume a particular solution that is a combination of the sine and cosine to easily capture the solution that this harmonic loading is giving us. And if we assume now a particular solution in this form, take note that we are not using a and b since a and b are used already in the first case. Then we can simply differentiate it twice and substitute it in this differential equation. We will now obtain a little bit complicated expression here, but all we need to do is to equate the terms in which the sine omega t are the same and solve for d. Okay, so what does that mean? So we simply make use of a one-to-one correspondence on all the terms that has a sine omega t, because the right hand side has a sine omega t. Then we capture all those which have this same form and equate those terms and solve for the value of d, or the value of the undetermined coefficient. And by doing so, we solve it easily, that d is equal to p all over m quantity omega squared minus big omega squared. So the small omega squared, the small omega rather, pertains to the frequency of this harmonic function, and the small omega, the big omega, pertains to the frequency of the harmonic function, and or the harmonic loading, and the small omega pertains to the frequency of your vibrating body. So the complete solution now becomes a combination of your complementary and the particular solution. And if we recall, this is now the free and damped case. Okay, so this is the case 1, the free and damped case, plus this is now the solution for this particular, okay, p over m omega squared, capital Omega squared, times sine omega t. So this is d times sine omega t. Okay, so this is now your assumed solution. Okay, this one, this particular solution. Okay, applying the stationary initial condition by doing a boundary value problem at time t equals 0, yo is 0, and vo equals 0, meaning to say that this is a stationary. Stationary means there is no initial displacement and there is no initial velocity. So if this is cosine, cosine of 0 is 1, sine of 0, this becomes 0. This all becomes 0, therefore a equals 0. And if we differentiate these ones to get the velocity, we get this equation and substitute the value of t equals 0 here. The sine of 0 is equal to 0, this is equal to 1, and this is equal to 1. So your b is simply equal to this negative p omega over m, then cosine of 0 is 1 times 1 time divided by omega squared minus capital Omega squared, then you put omega at the bottom to solve for b. So therefore y of t now becomes this particular solution, and this as your complementary solution, and this as your particular solution. Okay, okay, so this is a equals 0, this is now b is this one, okay, and this is plus p sine of t, yes, omega t here. Okay, so this is the particular yp, and this is the, because this has the b there, this is the complementary yc. And factoring it out, p over k, so where did k came from? We take note that k is equal to, omega is equal to the square root of k over m. Okay, square root of k over m. So take note of this such that your omega at the bottom is simply substituted by this k here. Okay, square root of k over m. Okay, so this is m omega m. So if we make use of this, omega squared m is equal to k omega squared m. So I think that there is a squared here. We will check this later, no? We'll check this out so that we can validate why is it that this becomes p over k. We simply divide this by omega squared, that's why this becomes 1 over, okay, so this was just divided by omega squared. There you are, okay. This was divided by omega squared. Okay, so if this is divided by omega squared, and then we factor out omega, so this is becomes m over omega squared, m over omega squared. Okay, so we'll check this out later, class. So take note that if this is a p over k, notice that for the stiffness equation in statics, the stiffness formula simply means that your p must be equal to the spring constant multiplied by, okay, the displacement. So y is equal to p over k is simply a static equation, and therefore this is a static equivalent multiplied by a dynamic magnification factor f of t equivalent to this whole value here. Hence, a dynamic displacement can be represented by a static displacement multiplied by what you call a dynamic magnification factor, equivalent to this, no? So in this case, this must fall on the subcase wherein the loading is harmonic. So if omega and small omega are equal, then we are to say that the system is the state of resonance, which is a very dangerous, okay? A state of resonance is a very dangerous situation. We don't want that to happen, okay? Why? Because if this is equal to that, this will become 1 minus 1, and everything divided by 0 is actually becomes very, very large or infinite. Okay, so the point here in deriving this equation is such that your frequency function, your forcing frequency, must not be equal to your natural frequency of vibration. So therefore, if that happens, resonance will happen, and since this is very dangerous, we expect structures to collapse. Okay, so for abrupt constant loading, we simply substitute a right hand term in terms of a constant term, and if we simplify this is an easier task to handle. And what did I tell you? This is now your particular solution, or sorry, your complementary solution, and this is your particular solution, y sub p, and the form, the solution actually takes the form of the right hand side here. Okay, so p over m is a constant, and p over k is also a constant here. So if we apply stationary conditions here at t equals 0, yo equals 0, and vo equals 0. So we simply come up with again a free an undamped, okay, case which has a particular solution and a complementary solution there. So we simply apply now the initial conditions at equals 0. This becomes 1, this becomes 0. Therefore, a is equal to negative p over k. And if we differentiate this once and apply again the boundary condition, this becomes 0 and this becomes 1, then b equals 0. Then your particular solution now becomes a cosine t plus p over k, and substituting the value of negative p over k, you get now this equation here. So this is now for abrupt constant loading. So for impulse loading, the equivalent to this is equivalent to a free vibration with yo equals 0 and the velocity equal to p delta t all over m. Okay, so if I have a velocity in meters per second, and then I have a force in kilogram meter per second square, okay, if I multiply this by time in seconds and divide this in mass, the mass is in kilograms, so I can cancel out actually the kilogram there, and the second here is cancelled, this becomes 1. So I have a meter per second on the right and a meter per second on the left. So I have a consistent unit here for the velocity. So this is very much applicable on blasting loads or bombing loads, no, wherein there's a delay upon which the wave occurrence will happen slightly after the explosion. Okay, so there's a delay here of tau such that your time is no longer equal to t, but rather t minus the phase the value of tau here. Okay, and notice that your p over k here, I'm referring to an equivalent free vibration case. So what is the a free vibration case here? So let's look into the final equation. Okay, free and damped vibration case. So I have this is the equation. Okay, if yo is 0, so it's your value is simply vo over omega sine omega t. So your vo is p delta t over m, okay, omega, then multiplied by sine of omega times your t now becomes t minus tau. Okay, so this is now your basis for this last impulse loading, okay, which is this one. Now for the general loading, the total response is simply the sum of individual responses to a differential loading similar to an impulse load. Okay, so again, this is just a summation of the complementary solution for a free undamped case, and then this is now an integral of the series of impulse loads based on this form or pattern. Okay, so if you notice, this is just a summation or an integral. I just place an integral sign there. Instead of having a p delta, I just place a function of t there, and then sine omega t minus tau. The m over w is constant, so we can put it outside and replace it by a p omega k value here. Okay, so this again, this is just done using the basic uh, relation of omega being equivalent to the square root of k all over the mass m. Okay, so that's it for now. In the force damp vibration, which is a little bit involved, I will be discussing this to you partially, not in full detail, because the mathematics of this requires a lot of identities, no, in terms of exponential and trigonometric. So I'll be giving you some insights on this on the next video. Thank you very much.